Good morning, Michael.
Good morning, Matt. Good to see you.
Good to see you again. So we're going to do our first application of what we've been studying, the best linear approximation, the slopes of things. And so we're going to apply it to max and min. So I'd like to start right from the beginning and say, what does this mean? What is max and min for objects in two dimensions if we're doing curves, in one dimension if we're doing curves?
So the idea is pretty straightforward. It can be a bit technical, but the basic idea is if you have a nice enough function, it always has a maximum value, which means it takes the value that is bigger than all the other points in the function, bigger than or equal to all the other points in the function. So a quick example is, see, if you have a function like this, you can sort of see there's a point here where the function is biggest. That's intuitively what we're talking about.
But if you didn't, like you've drawn a picture, we can follow the picture and actually look at this infinite collection of points and right away get the maximum. Vision tells us that. But now mathematically, how do we do this?
Well, there is a problem because, you know, functions can be very complicated. So what if you have something that like does all sorts of weird things and say, well, is the maximum here or maybe it's over here, something like that. So we have to be careful. And the very precise statement is if we have a continuous function, so f, it has to be continuous. And it has to be on an interval that's closed. So usually we write a closed interval like this, closed interval a, b. So it might be the interval from 0 to 1 or 1 to 100 or something like that. If f is continuous and it's on an interval, then it has a max. A maximum value.
Now, it's continuous, right? So that means we can compute the best linear approximation at any point in that interval. Is that right?
Say that again?
If this is continuous, then we can compute the best linear approximation, the slope of the derivative at any point?
Sadly, that's not true. So continuous functions don't always have derivatives. Okay, but what we can say is that the function only changes a little bit as we move back and forth between nearby points.
Okay.
Might not have a good linear approximation, which is what we meant by derivative. But what we do know is f doesn't change very much. So its value at x is going to be close to its value at x prime, as long as x and x prime are close to each other. Okay? So there is this question of why this should be true. So the maximum value is here, f at some point c. C is in between a and b. This is something kind of deep about real numbers. But I like to give this example. It's like, how do you catch a lion in Africa? Any idea?
Yeah, well, I'd start with the Sahara Desert and say, no, that's not going to be okay. So I start chopping Africa up and then narrowing it down to the regions where lions live. But then once I get to places like, I guess, Kenya or something, then I've still got all the area of Kenya to look at. That's a big area, and I've got to chop again. So keep chopping, 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 and eventually there he will be.
That's right. So you could imagine putting a fence around all of Kenya, say, you know there's a lion somewhere in there, so chop it in half, say which half is the lion in. So you put a fence up and say which half is the lion in. You've narrowed it down. Do that again in half, and half, and half, and half, until you have a cage about 1 meter by 1 meter. There'll be a lion in there for you.
But that's a very distinct lion, right? You don't have an infinite set of lions. But if we go back to this point, if we just take a small interval about that maximum, there's going to be infinitely many points. I can't look for infinitely many lions.
That's right, but that's why we're doing math. Okay, so the thing about trying to chase where the maximum is, you can imagine taking infinitely many points that get higher and higher. We don't know about this point yet. We don't know that it exists. But we have infinitely many points that get higher and higher. And what we can do is put an interval around them. And then we cut this interval in half and say, okay, which half do I still have infinitely many points? Because maybe here I only have 4 points, but the infinitely many are over there. So I'll take this interval, then I'll chop it in half, say which half has infinitely many points. Again, one of them has to have infinitely many, because if they both have only finitely many points, then I only started with finitely many points. So I keep on chopping and chopping and chopping, and this finally squeezes down to a single point, and that's going to be the point where the maximum is. That's the basic idea.
But can you evaluate that value? What if there's a curve that has a tiny, tiny hole in it?
Well, remember we said the function is continuous,
Oh,
and it's defined on an interval. So this point, f of c, it actually has to fill in
the hole.
the hole.
Ah, okay.
There we go.
Great. So now, can we go and use calculus as a tool to look at finding the maximum, minimum, and so on?
Well, this is exactly where the derivatives come in, okay? So if I give you some arbitrary function, really, really complicated, it maybe demonstrates how your neurons in your brain work. It might be a really, really messy function. And I want to say, where is the maximum? Could be at any of infinitely many points. But we can narrow it down to basically 3 cases where the maximum could be.
Oh, well, let's have a look graphically. What are those 3
So
cases?
here are the 3 cases. One easy case is when the minimum and the maximum just happen at the endpoints. Okay?
That's the easy one.
So these are endpoints. So you can just check the endpoints. And what's nice about endpoints is there's only 2 of them. So I don't have to evaluate the function at infinitely many places. It's just the endpoints.
Right.
Second point, you might have a function that has a weird kind of cusp or something. And that's where the derivative doesn't exist. So points where the derivative doesn't exist, those are candidates for maximum.
So if we take a look, we looked at this earlier, the rectangular hyperbola where you have an infinite asymptote. That's one of those cases. Here's one where you got cusps or corners, but also what about the asymptote case?
Well, remember, the function is continuous on an interval, so it can't have an asymptote. Okay?
Oh,
It's got to be
okay.
defined everywhere. So this is more like something like the absolute value of x. So this,
right.
here,
Yes.
this is 3, for instance. This might be 5 minus the absolute value of x minus 3 or something like that. Okay?
Right.
So absolute values have these funny things where you have little places where there's no derivative. So points where there's no derivatives is a possibility. Where derivative, can I use does not exist?
DNE. Okay.
DN, it does not exist.
And I guess the third one I got to guess is this one.
That's one. And what you notice here is this one. If I'm trying to find at this point here the best linear approximation, is it going to go up like this or down like this? Or what do you think would be my best linear approximation?
Well, it seems like this going up, 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 and if we go just to the left of that, still up, and then just to the right of it, it's down. So between up and down, you got nothing. It's flat.
That's right. So there,
It's
the
flat.
derivative is 0, so slope is 0.
So all we have to do then to find max and min is to look at these cases, decide which one we're in, and then act accordingly.
So this is the third case. Points where derivative equals 0. So you only really have to consider those 3 cases. So again, complicated function like something that's in your brain and does weird things. I only have to check it at the endpoints, check at places where the derivative doesn't exist, and check at points where the derivative is 0.
I guess from a mathematical point of view, you could have functions where the derivative doesn't exist at many, many points. But for realistic functions like what an engineer will have or what some kind of physical apparatus will measure, we won't be too far away from this case, and so we can use calculus to do it.
Should I do an easy example so we can see how it works?
Sure, let's do one.
So you were talking about easy examples that an engineer might run into. How about something like x cubed minus x?
Ah, sure.
I can plot this. I'm going to do it on the interval. Okay, well, we noticed that x equals 0, this function is equal to 0. Can you tell me another place where this function might equal 0?
Well, x cubed, the actual equation is equal to 0. So what, x squared, factor out an x,
Okay.
and we get x into x squared minus 1.
Okay, so x squared minus 1, when's that equal to 0?
Well, when x squared is equal to plus or minus 1.
Okay, so I've got 3 places where this thing is 0. Minus 1, plus 1. And I'm going to give you a little hint of what it looks like. It's a little, I missed. There. Goes through the origin.
Yeah, it's got to be an odd function, right?
Yeah.
So it's got that odd symmetry through 0.
And you can see right away, this is going to be a maximum, and that's going to be a minimum.
Yep.
So how do we find the actual value of that?
Well, we know how to do this. One of the first examples to compute the derivative of this function.
Right, so what's the derivative of this function? Should I put it down here?
3x squared minus 1 equals to 0.
So we take this, set this equal to 0. I can do that in my head. Can you do that in your head?
Yeah, x is equal to 1 over root plus or minus 1 over root 3. And the root 3 is, wait, what's root 3? Approximately
1.7, something like that.
1.7 something. So square root of 1.7, it is 1 over 1.7. So in very rough terms, around 1 over
Can I
1.
put, I'm going to cheat and say, I know
Yeah,
it's
1 over 1,
0.57.
that's what I was going to say. 1.7 is kind of close to 2, so roughly a half.
Roughly like that, yeah, so roughly a half, right? So that means this maximum is happening here at minus 0.57
And plus.
and plus.
Oh, good.
And see how easy that was to find where the maximum and minimum was happening. I just had a single equation set equal to 0 and solve. And that's why this is so useful. I didn't have to worry a whole lot about the details of this function. I just had to compute its derivative.
I like this, and especially right at the end. You know, there's great value to doing calculations in your head. A lost art, unfortunately. Thanks.
Thank you so much, Matt.